We've done radians, we've done angular velocity, we're doing centripetal acceleration. Yay. Our maths is advancing. We are becoming better physicists. In this whole series, I can't talk. Have you seen the first video? I go back and watch. Anyway, we're doing centripetal acceleration in this video, and we're going to explore some cool maths. Check out this tutorial for more info.
Alright, so let's discuss centripetal acceleration. You will have had to have watched our previous videos on centripetal force to completely understand this video, but let's just jump off from here. So we know that at any stage in circular motion, the linear velocity is always at a tangent to the circular path. Okay, and if we know that its instantaneous velocity, its speed, is going to be equal to its distance over time, and that for a single complete rotation, the distance travelled is going to be equal to the circumference, and the time taken is going to be equal to one time period, then we can take that information and we can say that the velocity is equal to 2 pi r, where 2 pi r is equal to obviously the circumference divided by big T, which is the time period, which I said is the time taken for one complete rotation. Okay? And then if we combine that with our previous equation, and if you don't recognize this equation, then you need to go back and watch our angular velocity video. But when you substitute those together, what you do is you end up with this equation, okay, where v is equal to r multiplied by omega, where v is the velocity, the linear velocity, and r is the radius, and omega is the angular velocity. Okay. So let's talk about how this links to centripetal acceleration, okay, and just keep these equations in your mind, okay, particularly this one here, okay. So the centripetal acceleration is defined as the acceleration of an object moving in a circular path at a constant speed, okay, and this applies to uniform circular motion only. You only cover uniform circular motion at A level, so don't worry too much about non-uniform circular motion. And similarly to centripetal force, it always acts to the center of the circle. We talked about how if we have a velocity which is acting like this, we talked about how the centripetal force is acting perpendicular to that velocity and how the acceleration is acting in that same direction as well. Okay, so it's always seeking the center. And the equation for centripetal acceleration is this, okay, where A is the acceleration, v is the velocity, okay, and r is the radius. So A equals v squared over r. And when you combine that with our previous equation of v is equal to r omega, that gives rise to this lovely equation where A is equal to omega squared r. Okay, this is probably one of the more important equations that you need to know in the topic of circular motion, and I think it's going to be helpful in the following example question. It's also worth noting before we get on to the question that depending on the type of situation that you're dealing with, provided that the centripetal force is constant in a situation, so if we were doing like spinning a roulette wheel on Earth, for example, for objects that have the same angular velocity, so they're subtending that circle at the same rate, the linear velocity at any moment of that object is going to be directly proportionate to the radius. Okay, so given that we know that, we can say that A out of these three objects is going to have the greatest linear velocity because it has the greatest radius. Okay, we can see that has the greatest radius. Whereas if we're dealing with a situation in which our centripetal force is not constant, okay, it isn't constant in this situation, we'll come to this equation in another video. So don't focus on that too much for now. We wouldn't say that A has the greatest centripetal force. Which one do you think it would be? I mean, if you think about this situation where we have the Earth, where is the gravitational attraction which is providing the centripetal force in this case going to be strongest? Well, it's going to be strongest here, right? The closer you get, the stronger it is. So in this case, it's actually C. So that's an important differentiation to make, okay? But you need to know both rules, okay, when you're going forward. But let's talk about how we can apply our knowledge of centripetal acceleration to a question like this. Okay, so the question says, calculate the centripetal acceleration of Mr. C, that's me, as he stands on the Earth's equator as it rotates. Okay, and it says that the Earth's radius is 6,370 kilometers, and the period of its rotation is 24 hours. Okay, so how might we tackle this question? Well, the first step is going to be to convert the orbital period from hours into seconds, okay, where we get 86,400 seconds. I'm sure you guys are happy with how to make this conversion. And the next step is to effectively decide which method we're using. Are we going to use A equals V squared over R, or are we going to use A equals omega squared R? And that's kind of a personal choice, right, at this point. So if we're using A equals V squared over R, then obviously we need to calculate V first because we have radius, okay, but we don't have either angular velocity or linear velocity. So if we're going to find linear velocity, we're using this equation that we talked about before, where V equals 2 pi R over T, okay, and otherwise we're going to be using this equation here, if we're using this method, where we're going to be saying that omega is 2 pi over T. Okay, I decided to use this one here, and I calculated for velocity. Note that I did convert my radius into meters. You can see that I made that conversion there. And then once I have my linear velocity, I just plug my numbers into A equals V squared over R, and this is the answer that you have. That is a 3, by the way. That's a 3. So 3.37 times 10 to the minus 2 meters per second squared. Okay, and that's how we can use our understanding of centripetal acceleration and apply it to an example question. Lots of information, but hopefully if you watch it again, then it will sink in and you will understand how it all clicks together.
Okay, hopefully that tutorial video helped you understand what centripetal acceleration is and the maths that's associated with it. In the meantime, please check out the previous videos in this series if you haven't already, and also please like and subscribe and share. It helps us grow the channel and get more content to you guys. But in the meantime, I'll see you next time. Bye.